Example 19.4 sees us finding several antiderivatives of functions. Now, the symbol that we use to find an antiderivative is this integral sign, the script S. So an antiderivative, or the family of antiderivatives of a function f of x, are all those functions who have lowercase f as a derivative. But of course, we can always add a constant, because that constant, when we differentiate, will just become 0. So if we shift a function up and down, it doesn't change the derivative. So this right here is the family of antiderivatives. Let's see what we mean. If I want to find the general antiderivative of x squared, I'm looking for the function which differentiates to x squared. So our function should be x cubed with a 1/3 out front. Let's double check. So if this is f of x, then f prime of x, right? If this is a good antiderivative, I should get back x squared. And I think we made the good choice, because when we differentiate capital F of x, the 3 drops down, cancels with the 1/3, and we have just x squared. So we got what we wanted. This capital F function is a good antiderivative, but we want the family of antiderivatives. So we should add a constant, because any function that looks like this will have x squared as a derivative. Let's do B. We want to find an antiderivative of the function 1/5 x cubed. So we go up power, so it's now x to the 4th. And we should divide by that 4, and we're already dividing by that 5. This is my contender for the antiderivative. Let's double check if we did it right. That's a little bit too big. If we take our antiderivative and differentiate it, we should get 1/5 x cubed. So the derivative of capital F, the 4 comes down, cancels with the 4 in the denominator. We have then a 1/5 x cubed, which is what we wanted. So capital F is a good antiderivative. Now we want the family of all antiderivatives. So if we shift this function up or down by a constant, they will always have 1/5 x cubed as a derivative. All right, now e to the 2x. We know there's an e to the 2x in there, because the derivative of e to the 2x is e to the 2x. But when I differentiate this, by my chain rule, I'll have to multiply by a 2, so I should divide by a 2. Let's double check if we did this right. The derivative of our antiderivative should be e to the 2x. And if we differentiate this, we have 1/2 e to the 2x, but then by the chain rule, multiplied by 2, the 1/2s cancel with the 2, we have e to the 2x, which is what we wanted. So this is a good antiderivative, and we want all of the antiderivatives, so we add a constant c.